On the 21st of June 2024, a telescope orbiting roughly 1 million miles from Earth spent 4 hours staring at one dim, unremarkable star. The star is called TWA7. It sits about 111 light-years away. It is smaller and cooler than our Sun, and it is only about 6.4 million years old. In stellar terms, that is a newborn. But the James Webb Space Telescope was not pointed there to admire it. The entire purpose of those 4 hours was to erase it, to block the star out completely and see what was left behind. And something was left behind. A single faint smudge of infrared light, sitting a tiny distance from the star, in a place where a hole had been carved through a ring of dust. Astronomers had been arguing for years that something had to be sitting in that exact spot. They had never seen it. Now there was a dot. Here is where this story gets more interesting than most headlines allowed. The team that found that dot did not announce a confirmed planet. They did the opposite. They spent most of their paper trying to prove it was something else. And when they finished, they published a number, about 0.34%. That is the chance they had been fooled. So what is actually sitting in that gap? Why does a Saturn-sized world matter more than the enormous planets we photographed a decade ago? And why, more than a year later, do the people who found it still refuse to use the word confirmed? You're watching Beyond the Signal, where we follow the evidence to the edge of what science knows. If you prefer space stories with the uncertainty left in rather than sanded off, subscribing genuinely helps this channel keep making them. To understand why one faint dot is a milestone, you first have to understand how badly we have been cheating. As of now, astronomers have confirmed more than 6,300 planets orbiting other stars. That number climbs almost every week. But look at how we found them. About 4,700 of them were found by the transit method, which means we never saw the planet at all. We watched a star, waited, and measured a fractional dip in its brightness as something crossed in front of it. Roughly 1,200 more were found by watching a star wobble as an unseen mass tugged on it. Both methods are indirect. Both give you real, rigorous science. Neither one gives you a picture. The count of planets discovered by imaging them directly, by collecting light that came from the planet itself, is about 98. Out of more than 6,300, fewer than 2 in every 100. There is a reason for that, and it comes down to 2 brutal numbers. The first is contrast. Even in the mid-infrared, where Webb is strongest, a star can be tens of thousands of times brighter than the object next to it. The second is angle. The gap between star and planet, as seen from here, is measured in arcseconds. 1 arcsecond is roughly the width of a dime viewed from 2 miles away. So the real task is this. Find something 10,000 to 100,000 times fainter than a light source, sitting a dime's width away from it from 2 miles back. That is why every exoplanet ever directly imaged before this one was, frankly, an easy case. They were young, they were enormous, and they were still glowing with the leftover heat of their own formation. Most were between 2 and 10 times the mass of Jupiter. Those are the planets that shout. Everything quieter than that was simply below the floor of what our instruments could reach. Which brings us to the dust. TWA7 is surrounded by a debris disk. That is the term for what a planetary system looks like after the gas is gone. The primordial cloud has dissipated, and what remains is rock and dust, continuously ground finer by collisions between larger bodies. Our own solar system has a faint version of one. Think of it as construction debris left over after the building is finished. The disk around TWA7 was first resolved by the Hubble Space Telescope decades ago, and later mapped in much finer detail by an instrument called SPHERE on the European Southern Observatory's Very Large Telescope in Chile. What those observations showed was not a smooth cloud, it was structure. A broad inner ring peaking around 28 astronomical units from the star, a remarkably narrow ring at about 52 astronomical units. A wider outer structure near 93. 1 astronomical unit is the distance from the Earth to the Sun, about 93 million miles. So that middle ring sits nearly 5 billion miles out from its star, well beyond where Neptune orbits in our system. And between those rings were gaps. Clean, empty lanes. In planetary science, gaps like that are treated as evidence of gravity at work. A planet moving through a field of debris does not just orbit, it sweeps. It removes material along its path and confines what is left into sharp edges. For decades, astronomers have used disk structure as a fingerprint, reading the gaps and calculating the mass and orbit of the planet that would have to exist to produce them. Only once had that prediction ever been cashed in. Around the star Beta Pictoris, a warp in the disk was used to argue for a planet, and eventually that planet was imaged. Everywhere else, the fingerprints were there, and the suspect was missing. There was a specific reason to think TWA7 was the best place to try again. Its disk is oriented almost face-on to us, tilted only about 13 degrees. We are looking straight down at the whole system, like looking at a target rather than the edge of a plate. Ground-based instruments could rule out anything heavier than roughly 0.5 to 1 Jupiter masses beyond 50 astronomical units. If a planet was there, it was smaller than that, and nobody had an instrument sensitive enough to go lower. Then Webb was given 4 hours. The observation used MIRI, the mid-infrared instrument, through a filter centered at 11.3 microns. That wavelength choice is the first piece of quiet strategy in this story. TWA7 is a small, cool red dwarf. At 11 microns, it is not as overwhelming as a sun-like star would be. But a young planet, still radiating the heat of its own formation, glows relatively well there. In the mid-infrared, the gap between star and planet narrows. Not enough to make the job easy, just enough to make it possible. The second piece is the coronagraph. That word simply means a device inside the telescope built to eliminate the light of the star you are pointing at. Webb's version for this observation is called a 4-quadrant phase mask. It splits the incoming starlight into 4 sections and shifts them so that they cancel each other out using interference. Light waves, pushed out of step, erase each other. The star's central glare collapses. Everything nearby survives. That is elegant, and it is still not sufficient. Some starlight always leaks around the mask in a complicated pattern. So the team did something less glamorous and more important. They pointed the telescope at a second, similar star, one with no known companions, and recorded that leakage pattern with a 9-point dithering sequence. That gave them a template of what pure glare looks like. Subtract the template from the science image, and what remains should be only the things that actually exist around TWA7. They also observed the target twice, rotating the telescope slightly between the two 2-hour exposures. Real objects in the sky rotate with the field. Optical artifacts do not. It is a way of asking the same question twice from 2 angles. When the subtraction was done, 3 sources appeared within 10 arcseconds of the star. 2 of them were quickly explained. One was a background star, already visible in older Hubble and ground-based data. The second was a resolved object about 6.7 arcseconds to the east, invisible in the near-infrared but matching a bright source seen by the ALMA radio array in Chile back in 2016. That combination, bright in the mid-infrared and radio, absent in the near-infrared, is the signature of a heavily reddened, distant galaxy. Interesting, but not what they came for. The third source was different. It sat about 1.5 arcseconds northwest of the star. It appeared nowhere in the Hubble data, nowhere in the Sphere data, nowhere in ALMA's maps. It existed only in Webb's mid-infrared frames, with a signal-to-noise ratio of 30 in the stronger of the 2 rolls. Extremely red, extremely faint, about 22 microjanskis of flux. And it was sitting inside the ring at 52 astronomical units, in exactly the underdense patch where the disk models said a planet should be. Now look at what the team did next, because this is the part that separates science from a headline. They tried to kill it. Option 1, something in our own solar system drifting through the frame. A distant asteroid or dwarf planet would leave a trail across a 2-hour exposure or shift position between the 2 rolls taken hours apart. This object moved less than about 0.05 arcseconds per hour, which is essentially not at all. To be that slow, a solar system object would have to sit more than 200 astronomical units out, and to be that bright at 11 microns, it would need to be roughly Neptune-sized. The team even checked whether it could be the hypothetical Planet 9, the proposed distant world some researchers invoke to explain the orbits of far-flung objects. Based on published constraints and predicted orbits, that was ruled out. Option 2, a background galaxy that happened to be in the way. This is the one that keeps astronomers honest, because it has embarrassed people before. The team took every constraint they had, the brightness at 11 microns, the non-detection by ALMA, the non-detection by Sphere in the near-infrared, and tested them against 14 template spectra for star-forming galaxies and active galactic nuclei across a range of distances. Then they folded in real galaxy counts from deep Webb surveys. The result: the odds of finding a galaxy that satisfies all 3 constraints inside a circle 1.5 arcseconds in radius around this specific star came out to about 0.34%, with an uncertainty of a few tenths of a percent either way. Low, not 0. Keep that number in mind because it becomes the whole argument later. Option 3, a planet. 2 independent models were run. One fit the atmosphere directly, including water clouds, and landed on an effective temperature between 305 and 335 Kelvin and a mass near 0.3 times Jupiter. The other used thermal evolution models for cold, low-mass planets and came back with essentially the same answer, translated into planar terms, roughly 100 times the mass of Earth. That is about one Saturn. And a temperature near 320 Kelvin, which is about 47 degrees Celsius or 117 degrees Fahrenheit. That number surprises people. It sounds like a warm afternoon, not a frozen outer world. But that heat is not coming from the star. At 52 astronomical units, the star delivers almost nothing. What we are measuring is the object's own leftover warmth from forming a few million years ago. This is not a planet being heated. This is a planet cooling down, and we caught it while it is still glowing. Then came the test that makes the case genuinely hard to dismiss. A separate simulation was run, tracking 200,000 hypothetical debris particles distributed between 20 and 130 astronomical units, with a single planet of 0.34 Jupiter masses placed at 52, orbiting a star of 0.46 solar masses, evolved forward for 10 million years. The simulation cleared out a wide zone. It left behind a narrow ring at 52 astronomical units, and it produced one more feature that nobody put in by hand, a relative void in that ring, right at the planet's position, with material bunched ahead of it and behind it. That is a co-orbital resonance. In our solar system, we already know what it looks like. Jupiter has two vast swarms of asteroids called the Trojans, locked into stable pockets that lead and trail the planet along its orbit. They travel with Jupiter without ever colliding with it. The simulated disk around TWA7 produced the same architecture, and the real disk, as imaged from Chile, shows the same underdensity in the same place. So the argument was never a single dot. It was a dot in the predicted location with the predicted brightness and color of the predicted mass, producing the exact disk structure that was used to predict it in the first place. The results were published on the 25th of June 2025 in the journal Nature. There is one problem. The object is still officially a candidate. Not because anyone thinks the analysis was sloppy, because one specific test has not been run yet. In direct imaging, the gold standard for proving something orbits a star is common proper motion. Every star drifts across our sky. TWA7 drifts about 0.12 arcseconds per year. A background galaxy stays put. A real companion travels with the star. At the time of the discovery, there was no second epoch to compare. One observation cannot measure motion. And this planet's orbit takes roughly 550 years to complete a single lap, which means it will barely shift within its own orbit during a human career. The star's own drift, however, adds up quickly. Within a few years, the separation between star and background objects becomes obvious. That is the honest state of things. The evidence points in one direction, but the case is not closed by the standard the field uses. There is also a softer uncertainty worth naming. The mass estimate assumes the planet formed at the same time as its star. If it formed later, it would be even lighter than 0.3 Jupiter masses. And the atmospheric fits require a metal content above solar, which nobody can yet pin down without a spectrum. Since then, a follow-up did arrive. A separate team, led by Katie Krotz, observed the same system with Webb's NIRCam instrument at shorter wavelengths and published in the Astrophysical Journal Letters. They recovered most of the disk structures, and in one filter, they detected two faint sources at a confidence level between 2 and 3 sigma. Sigma is just a way of stating how unlikely a signal is to be random noise. In astronomy, 5 sigma is the threshold for calling something a detection. 3 sigma is a strong hint. So these were hints, not proof. But one of those hints sat at the same position as the original MIRI source. An independent instrument, a different wavelength, the same spot. That pushes the interpretation further toward a genuine sub-Jupiter mass planet and further away from a background galaxy. The second faint source has not been explained at all yet, which means TWA7 has now become only the second system in history, after Beta Pictoris, where a planet predicted from the shape of a disk was subsequently found sitting where the prediction said it would be. So, why does this specific dot matter more than the giant worlds we photographed years ago? Because of where the floor moved. Every exoplanet directly imaged before this one was at least 10 times heavier. Not 10% heavier, 10 times. And in the same paper, the team stated that with these observations, objects as light as 25 to 30 Earth masses could have been detected at that separation if they had been there. That is roughly Neptune territory. Sitting in that sentence is the entire reason astronomers reacted the way they did. A method that could only see the loudest, largest objects in a planetary system has just been shown to reach into the range where the planets of our own solar system live. Now let me be equally clear about what this is not. This is not a habitable world. It is a cold gas planet, nearly 5 billion miles from a dim red dwarf, with no solid surface worth standing on. There is no biology in this story, no signal, no atmosphere anyone claims is breathable. Anyone selling this discovery as a step toward finding life is skipping several decades of work. It is also not a photograph in the way most people picture one. Nobody opened a shutter and got a portrait. What exists is a measurement of infrared photons at 11.3 microns with a modeled starlight pattern mathematically removed, rendered as a bright point in a processed frame. The light is real and it came from the object. The image is an image, but it is a data product, and the honest label on it is candidate, not confirmed. That distinction is not pedantry, and recent history proves it. Consider K2, 1, 8b, a world about 124 light-years away. In 2023 and again in 2025, teams reported a possible detection of dimethyl sulfide in its atmosphere, a gas that on Earth is produced almost entirely by marine life. The coverage was enormous. Then a broader reanalysis led by researchers at NASA's Jet Propulsion Laboratory, involving multiple independent teams and including the original authors, found the signal sitting near 2.7 sigma, below the threshold. They also showed that ordinary photochemistry in a hydrogen-rich atmosphere can manufacture the same molecule with no biology at all. The planet is still fascinating. Water-rich, methane, and carbon dioxide present. Genuinely worth studying. But the biosignature claim did not survive contact with more data and more scrutiny. That is the environment TWA7b is entering, and it is why the careful language around it is a strength rather than a hedge. So what happens next? Two things. The first is more Webb, additional photometry, and, ideally, spectroscopy of this object. Because it is well separated from its star on the sky, it is an unusually good target for that. A cold, non-irradiated, sub-Jupiter mass world with a real spectrum would let astronomers compare it directly against Saturn and Jupiter, which we know intimately, and against the handful of other cold-imaged objects, like the roughly 275 Kelvin planet around Epsilon Indi, which is about 6 Jupiter masses. The second is bigger glass. The extremely large telescope is under construction on a mountain in Chile's Atacama Desert, with a primary mirror 39 meters across, larger than any optical telescope ever built. Its schedule slipped, and it is worth stating the current version rather than the optimistic one. Telescope first light is now planned for March 2029, with the first scientific observations expected in December 2030. And beyond that, the Habitable Worlds Observatory, a mission designed specifically to take direct images and spectra of Earth-sized planets in the habitable zones of nearby stars. That one is not expected to launch until the 2040s, which tells you exactly what TWA7b is. It is not the destination, it is the calibration. There is one detail in this story I keep coming back to. The infrared light that produced this detection left that object about 111 years before Webb collected it, not as a figure of speech. Light years measure distance, and 111 light years means 111 years in transit. The photons that landed on Webb's mirror in June 2024 departed somewhere around 1913, when powered flight was a decade old and radio was a novelty. They crossed the space between stars for a century, arrived at a 21-foot golden mirror, parked 1 million miles from Earth, passed through a mask engineered to destroy the light of a star, and registered as 22 microjanskis of flux in a detector cooled to within a few degrees of absolute zero. Then a human being ran a subtraction and noticed a dot where a model said one should be. Think about what that means about the position we are in. For all of recorded history, other planetary systems were an inference. Then, for 30 years, they were statistics. Thousands of confirmed worlds we could count but never look at. Now, for a narrow set of nearby young systems, we can point an instrument and collect their light. And there is something almost humbling about the timescales involved. This planet takes about 550 years to circle its star once. Nobody alive will see it complete a single orbit. Whatever we learn about it will be assembled from snapshots by people who never overlap, each one adding a few years of measurements to a record none of them will finish. The person who eventually takes a direct image of a rocky, temperate world around another star is almost certainly in school right now, and the method they use will trace back through this observation, and through the sensitivity limits it established, and through 0.34%. So here is what we know. On the 21st of June, 2024, Webb's mid-infrared coronagraph detected a faint, extremely red point source, 1.5 arcseconds, from the young star TWA7, sitting inside a gap in a dust ring where models had predicted a planet. Its brightness, color, position, and inferred temperature, near 320 Kelvin, are consistent with a cold world of roughly 100 Earth masses, about 1 Saturn. A dynamical simulation using that mass at that distance reproduces the disk's narrow ring and its co-orbital void. A follow-up with a second instrument recovered a marginal signal at the same location. Here is what changed. The floor of what direct imaging can reach dropped by a factor of at least 10 into the range where our own solar system's planets live. And for the second time ever, a planet predicted from the sculpting of a disk was found where the prediction pointed. Here is what we still do not know: whether the object shares the star's motion across the sky, which is the test that will settle its status; what its atmosphere is actually made of; what the second faint source in the NIRCam data is; and whether the 0.34% turns out to be the one time in 300 that the unlikely answer was the right one. That last possibility is not a weakness in the story. It is the reason the story is worth telling. The measurement was published with its own failure probability attached, out in the open, for anyone to check. Tell me which part of this landed hardest for you: the fact that the planet was predicted before it was seen, or the fact that the people who found it still will not call it confirmed. This is beyond the signal. Keep looking past the obvious.